Welcome to aminacademy.com. In physics, let us discuss about thin lenses. What is thin lens? A piece of glass of finite thickness with two spherical boundaries is a lens. If the thickness of the lens is much smaller than the diameter of the lens, we call it as thin lens. Here, diameter of the spherical boundaries is very greater than the thickness of the lens, then it's called thin lenses. Types of thin lenses. Lenses may be divided broadly into two main types, convex and concave. Lenses that are thicker at their centers than at their edges are convex. This is a convex lens because thinner at center, thicker at outer. A light beam passes through a convex lens is focused by the lens on a point on the other side of the lens. Here, this is a concave lens is thinner at center, thicker at outer. Here, thicker at center, thinner at boundaries. That is called convex lenses. Here, look at here. In this convex lens is called converging lens. That means the rays come parallel and fall on a lens surface and focused on other side at focus point. So it's a converging. The lines are converging. Optical lines are converging. Diverging lenses, look at here. Suppose a ray is falling parallel and it diverge like. So it's called that rays are diverging. So this is called a diverging lens. Now let us discuss about objects and image relation in lenses. First we consider about convex lenses, then different position of the object and that respective position on image we will discuss now. Here, suppose when an object is placed at infinity, this very far distance, the object is there. That means the rays are coming from very far, and what happened to that rays? When the object is placed at infinity, the real image is formed at the focus. So it's converging and at the real image is formed at the focus point here. The size of the image is highly diminished and point size. Look here, this point size here. Next one, when an object is placed beyond the center of the curvature, that is here 2f is the center of the curvature, little beyond that object is placed here, then what happened to that lens here? When an object is placed beyond the center of curvature, the real image is formed between the center of the curvature and focus. So here image is formed here between the focus and the center of the lens. So object is here. The image size will not be the same as the object. It will be diminished in size. It's a AB is lesser height than A dash B dash. Next one. When an object is the center, that is center of the lens, that is object is at 2f, so the image also at 2f. Look at here. The real image is formed at the other center of curvature. The size of the image is the same as compared to that of the object. Look at here. Always remember the rays parallel to the main axis and it pass through the center of the curvature. And one more, suppose the rays if pass through the center of the lens, it comes as it is a straight line and both rays intersect at the point here. So this is a image is at same distance from the center where the object is placed, also the same size when object is at 2f. Next one, an object is between 2f and f. What happened? So the same procedure, the rays passes parallel to the axis and go through F2, and another ray passes through the center, and then both rays intersect here. So this is a image size is little taller than object size, as well it's inverted. When an object is placed between the center of the curvature and focus, the real image is formed behind the center of the curvature. The size of the image is larger than that of the object. Next, when object is at F, at focus point, the object is kept here. Then when an object is placed at the focus, a real image is formed at infinity. So look at here, a ray parallel to the axis and pass through the focus. Another ray pass through the center and it never meet. It's parallel. That means when an object is placed at the focus, the real image is formed at infinity. Real image is formed at infinity. The size of the image is much larger than that of the object. Next here, when further we'll discuss here. Suppose the object is kept between F1, then center of the lens, we can draw that it becomes still larger size. We can get it at this image. Here, this is an object is kept at that between F and center of the lens. What happened? Same procedure. Ray go and pass through another focus, and another ray pass through the center and come back. So what happened? This imaginary image is formed here. When an object is placed in between the focus and optical center, the virtual image is formed. The virtual image is formed. The size of the image is larger than that of the object. Next, same that object and image relation in lenses, in concave lenses. You know the concave lenses is here, that is at center is thinner, at outer it is thick. If you look at an object through a concave lens, it will look smaller and closer. Look at here. Here the object and same procedure, ray is passing and go like and passes back through F. So the object inside the focal point. Here this object is here, it formed. Here suppose that object is beyond F. Object is beyond F. If you move the object further out, the image will not move as much. The image will not move as much. Most probably size of the same image here. Now what we discussed in the position of the image and the object, distances and type of image and size of image in the tabular form we can do here. Look at here. First, concave lenses. First one at infinity. Position of the infinity. We know that the position of image is at the focus. Size of the image is highly diminished, point sized, and nature of image is virtual and erect. Like here in concave lenses we are doing. Next one, between the infinity and optical center, that in between focus and optical center, diminished, virtual and erect. Next here, in convex lenses, the positions are more here. First, at infinity, what happened? That image position of the image is at focus, size of the image is highly diminished, point sized, real and inverted image. Like one by one, we can at infinity, beyond 2f, at 2f, these are object positions. At 2f, between f and 2f, at the focus f, between the focus f and optical center s. So these are the different positions. Now, next we will discuss about object and image relation formula for lenses. Here we know this formula. We'll write one more time here. 1 by u plus 1 by v equal 1 by f. In this, we know that u equal object distance from center of the lens, and v image distance from the center of the lens. F is focal length. Here, object distance is positive for a real object and negative for virtual object. You have to keep object, if it is positive position, it's a real, if it is real object, and negative for virtual object. Same, V is image is in positive real axis and negative for the virtual. F also same, if F is positive for a converging lens and negative for the diverging lens. Now, linear magnification. What is linear magnification? Is size of linear magnification is size of image over size of object. Is further V over U. It's called a linear magnification. You have to keep modulus. For positive or negative, it gives the positive answer only. Converging lenses form inverted and real image of object located outside the principal focus. When the object is between the principal focus and the lens, the image is virtual on the same side of the lens as the object, erect and enlarged. Next one, diverging lenses produces only virtual, erect and smaller images of real object. Diverging lenses, that is concave lenses, produce only virtual, erect and smaller image of real objects. Next one, lens maker's equation. What is lens maker's equation? Equal to 1 over f equal n minus 1 over r1 minus 1 over r2, where n is the refractive index, n equal refractive index, n1, n is the refractive index. Next, r1 and r2 are the radii of curvature of two lens surfaces. r1 and r2 are two radii of curvatures of the two lens surfaces. Lens surfaces, because one lens have two surfaces. These are equal. That means these are r1 and r2. These two r1, mostly the r1 and r2 won't be equal. Next one, if the lens with refractive index N1 is immersed in a material with index N2, then N is a lens maker's equation to be replaced by N1 over N2. Now, lens power. What is lens power? Is in diopters, that is per meter, is equal to 1 over f. Lens power is always 1 over f in diopters, diopters, which means per meter. Diopters, this unit is diopters, where f is a focal length. F equal to focal length. Next is lenses in contact. That means one or two lenses in contact. What happened? When two thin lenses having focal length f1 and f2 are in close contact, the focal length f of the combination is 1 over f equal 1 over f1 plus 1 over f2. That means if here two lenses are close contact with them, then f is 1 over f is equal 1 over f1 plus 1 over f2, where f1 is the focal length of the first lens and f2 is the focal length of second lens. f1 is focal length of first lens and f2 equal focal length of second lens. F is the focal length of combination. Combined lens. So far we discussed about lens, what are the types and what are the positions and image distances, and lens power, lens maker's equation, like we have done. Please subscribe our YouTube channel.